So hopefully you have now used a function to find the values for delta t equals 0.005. And I just interpreted this delta t to be the delta t that we're working with currently, which is half the length of the interval. I think I was a little ambiguous about that, but it doesn't matter. It doesn't really affect the result. So here's my table based on that delta t is half of the time interval. All right, and so I see these values, and we had observed before that the velocity is approaching negative 2193.75. I see here very clearly that that trend is showing with my smaller and smaller values of delta t. In fact, it looks like I get my final value to actually be the velocity that we think we're approaching. So one thing that I do is to point out that that is impossible. This value cannot be exactly 2193.75. So if you have not thought about why that's impossible yet, take a moment, pause the video, and think about how come, my calculator clearly did y3 of 0.0001 and got negative 2193.75. I'm saying that's impossible. Now, I'm not asking you why the calculator could come up with that, because obviously it has to do with rounding, okay? But how is it that I know that that number cannot be right, cannot be exactly right? Think about that. All right, so the reason is that negative 2193.75 is the value that we get if delta t is 0. All right, we get negative 2193.75. But these two values cannot be the same. They cannot be, right? Because if you look at this function, it depends on delta t squared. So the value for delta t being 0 cannot be the same as any value for delta t that is non-zero, all right? But see, we're already getting close to that concept of what is a non-zero number and how close can we get to 0 with a non-zero positive number. So we can't use delta t equals 0, but we can get closer and closer to delta t equals 0. And the question is, how close can we get? How small a number can we use for delta t that is not 0? What is the smallest number, in fact, that we could use that's not 0 that we could use for delta t? Well, look how everything has looped back to the question we started this class with. What is the smallest number, delta t, that is positive but not 0? What is the smallest positive real number? There isn't one. All right? So where is the end to this process where we get closer and closer to negative 2193.75, but we never quite get there? All right? But there is no end to that process. We can go on infinitely with the process and become infinitesimally close to the actual value. Now, in mathematics, we have a tool that we're going to develop that's called a limit that will allow us to resolve the problem of how I can have these delta t's that are as close as you can get to 0 without actually being 0. And there's a lot you can sort of say about it. But let's come back. So never trust your calculator again, okay? No matter what anybody comes up with, they're going to get quantum computers pretty soon. Not as good as the one inside your cranium. Your brain's got a calculator that is based on learning neural networks that are, soaked in chemicals. You can't get better than that. All right. What value does... So this is developing the kind of language that we're going to use when we talk about what are called limits. This is limits number 1. This is the kind of language we're going to use. What value does r of delta t approach as delta t approaches 0? Well, r of delta t approaches negative 2193.75 as t approaches 0. So we actually have a way of writing that. We can say r of delta t approaches negative 2193.75 as delta t approaches 0. That's the kind of language we use for limits. Do you think that that is a good value for the exact speed of the probe? Do you think if we use that value for the probe, no matter what our error tolerances are, the probe's going to pop the parachute at the right time and going to land safely? Yes. The answer to that is yes. Yes, it is. Even Fela thinks it is. All right, is this the same value that we get from substituting delta t equals 0? Well, yes. Yes, it is. Is it mathematically legitimate to do so? Not yet. All right, so as we understand, when we're looking at this rational expression, you cannot substitute delta t equals 0. When we do the simplification, there is a domain change, right? Change in domain. I kind of glossed over that phrase, but this is what it means. The delta t cannot be equal to 0 in this expression. So it's not mathematically legitimate to substitute that delta t equals 0 in either of these expressions. But when we develop a thing called a limit, then it will be legitimate to do so. All right, now, can you describe the difference between average speed and instantaneous speed? That's our goal. That's something you should think about. Hopefully you've written something down. If you haven't, pause and write an answer to that question. But basically, I'll tell you now, that average speed is the speed over a non-zero time interval. And it's defined by f of b minus f of a over b minus a. The instantaneous speed is over a 0 time interval, or you could say no time at all. No time, right? It's at an instant, as the name implies, at an instant. Right? And you can't use this formula for it. You need a limit of something. So what is this idea of a limit? What I've worked on now is giving you some motivation of what limits are about, why we care about them. Limits are going to give the answer to how we do an instantaneous speed, and we're going to talk a lot more about that for the next 5 months. So your next job is to do part 2 of this. So we've now gone through all of part 1, and we've got all the answers to that, and I gave you some hints and assistance as we went through. Hopefully you figured out a lot of it on your own. Now you're going to do part 2. So a lot of the terminology is similar. We're finding average rate of change over different time intervals. So think about how we did that. I did the time intervals differently this time. This time they're not all centered at the same. They all have a right endpoint of 4. How is that going to change our mathematics? You look and see how we set it up here. Do a substitution like we suggested. It tells you to factor out delta t. So this is going to use very similar steps. Develop a chart. What is an approach? It's going to use very similar steps that we did here. So think about the things that we did in part 1, but it is not going to be exactly the same as part 1. So there you go. That's your job. Your homework to do totally on your own is part 2 about the chemist. Enjoy.